Okay, so then let's look at the convergence algorithm convergence analysis for the smoothing technique. So in the previous lectures, we talked about the smoothing technique, but there are two approaches. One is through this moral envelope. And this is a systematic way to construct a smooth approximation of a function. The second one is via this conjugation. If the function can be written as the conjugate of another function, then we can add a small perturbation to the conjugate function, and that will create a smooth approximation. So these are the approaches to construct a smooth approximation of a given non-smooth function. And then let's consider this composite optimization problem. Well, this f is a both of these two are convex functions, but f is not differentiable. F is non-smooth, but it is smoothable. It is alpha beta smoothable. And H is the convex regularizer. It is not differentiable. It may not be differentiable. So this is different from the composite problem that we studied in proximal gradient method. There we have a smooth objective function f. So here f is not non-smooth, but it is alpha beta smoothable. So we can consider replace this f by its smooth approximation. Once we do that, this part will become smooth function. And then we are looking at the smooth plus a non-smooth optimization. So we can do proximal gradient descent. So the idea is very simple. We first build f sub mu. This is a smooth 1/mu smooth approximation of the original function f. And we smooth this one with parameters alpha and beta because it is alpha beta smoothable. And you can construct this f mu either by moral envelope or by conjugation, by the conjugation approach. So here we assume that we can obtain this f mu. Once we have this f mu, then we will replace this f by f mu. So we are going to minimize f mu plus h. And for this problem, it is smooth. This is a smooth problem plus a non-smooth regularizer. So we can do proximal gradient descent on this problem. So this is the accelerated proximal gradient descent applied to this problem. So the first step is gradient descent on f mu. Second step is the extrapolation step, momentum step. And then we want to analyze the convergence guarantee of this approach. And this approach would be, the analysis would be different because here, on one hand, this accelerated algorithm is applied to solve this composite problem. Right. So we can imagine that this algorithm will converge to the solution of this problem. at a very fast rate, this accelerated gradient descent. However, this problem is not the original problem that we want to study. The original problem that we want to study is this one. Well, we have f instead of f mu. So therefore, we are applying this accelerated method to a smooth approximation. But this problem is slightly different from the original problem. So their optimal solution will also be different. And we need to characterize this kind of approximation error. There's an approximation error between these two. And then we have this informal result. We suppose we want to achieve an epsilon accuracy for the original problem. Okay. So this fxt minus this fopt is the minimum value of f. The optimality gap is bounded by epsilon. So suppose we want to achieve a target accuracy epsilon. So this f is defined. This f corresponds to the objective function of our original problem. It's h, is f plus h. So our goal is to achieve epsilon accuracy on the original problem. Okay, this is our goal, ultimate goal. Okay, now you set a target accuracy epsilon, then you set an approximation parameter mu to be epsilon over beta. Right. So this mu is the smoothing parameter. You choose this parameter to be epsilon over 2 beta. Well, beta is here alpha and beta is the smoothing parameter because we assume this f is alpha beta smoothable. Okay. So these are these two parameters. So you pick such a smoothing parameter mu, and then run this algorithm for many iterations, right? And this result says that if you run this algorithm for this many iterations, at least this many iterations, right? Square root of alpha beta divided by epsilon. Then the solution would be, then we will obtain an epsilon accurate solution. So you see this result is slightly different from the previous analysis of those optimization algorithms. So if you look at this algorithm is applied to solve this approximated problem. Okay, so let's call this f sub mu. So the optimization, we can apply the optimization result of accelerated gradient descent on f mu. Right, but here in this result is stated in terms of the optimality gap of the original problem. So we need to consider both parts. One is the optimization, applying accelerated gradient method to optimize this approximated problem, and then consider the approximation error. Combining two parts, we can get this this result. Okay. So before we dive into the proof of this result, let's look at the implications of this convergence rate result. This result says that if your f is alpha beta smoothable, then we can choose to smooth it using this parameter mu. Okay. And then let's run accelerated gradient descent on the smooth problem for these many iterations. Once we run it for these many iterations, we are guaranteed to get an epsilon accurate solution. So roughly speaking, in order to get an epsilon accurate solution of the original problem, we need to run this many iterations of accelerated gradient steps. Therefore, the iteration complexity is basically 1 over epsilon. Right? It's a constant divided by epsilon. And this complexity is better than applying subgradient method directly to the original problem. For subgradient method applied to this original problem, the complexity is 1 over epsilon squared. So this approach, smoothing approach, will be better than the subgradient approach. Okay. So now let's look at the analysis of this algorithm. First, note that we applied the accelerated method. Right, so this is our algorithm. And this algorithm is to optimize the smooth problem. So this algorithm is directly optimizing this problem. And this is a smooth convex composite optimization problem. So we can directly apply the convergence rate result of accelerated gradient descent to this problem. Okay. Therefore, to obtain an epsilon over 2 accuracy for this smooth problem, we need this many number of iterations. These results are follows from the previous lectures on accelerated gradient descent, where the complexity is 1 over square root of epsilon. Right. So here we are in the first sentence, right? We are obtaining an epsilon over 2 accurate solution of the smooth problem. Okay. Because the algorithm is working on this smooth problem. Okay. Now, once we achieve a epsilon over 2 accurate solution of the smooth problem, we want to further understand how far this solution is from the optimal solution of the original problem. So we will consider this approximation error. Because more specifically, because F mu is a smooth version of F. So by the definition of alpha beta smoothable, the gap between these two is controlled by beta times mu, by the definition of alpha beta smoothable. Therefore, we want to make sure this approximation error is also small. So let's set this error to be epsilon over 2. Okay. Once you set this error to be epsilon over 2, we are guaranteed that the approximation error of F is bounded by epsilon over 2. And then now we can look at the optimality gap of the original problem. This is capital F. And this one can be decomposed This one can be decomposed into two parts. One is the approximation error of the function f. Because if you compare this original problem with the smoother problem, the only difference is in the f part. We only smooth the f part. So we can decompose it as a approximation error plus an optimization error. And now both of these two parts are bounded by epsilon over 2. Right. Therefore, the overall optimality gap is bounded by epsilon. Okay. So this proves the claim. So in order to get an epsilon accurate solution for the original problem, we need the first two bullet points. The first bullet point is to run the algorithm, run accelerated gradient descent on this smooth problem. And we need to run this many iterations to get an epsilon over 2 accurate solution. And then the second thing is to control these smoothing parameters, control this mu so that the approximation error is small enough. It is bounded by epsilon over 2. But once you have a good optimization solution plus a small approximation error, putting these two together will guarantee a small optimization error for the original problem. So the overall iteration complexity is given by this one. It's given here. But in this case, this mu depends on epsilon, because in the second point, we need to pick mu small so that it can control the approximation error properly. So plug in this choice of mu into this complexity bound, we get this one. So eventually we have square root of alpha beta over epsilon. So you can see there's a trade-off between these two bullet points. If we choose a very small mu, we will have a very accurate approximation. The approximation error will be small. However, a very small mu will make the first term very large. This complexity will goes up, because if we use the very small mu, then the condition number of this problem will be very bad, and that increases the complexity. If we choose a very large mu, then this problem would be very smooth, will be a well-conditioned problem, and then the complexity will be relatively low. However, the approximation error will be big, because the approximation error depends on mu, scales as beta times mu. So these parameters are chosen in the way to balance these two errors, and in the end, to achieve this improved complexities. Right. So when we analyze these smoothing techniques, we always need to consider these two parts. The optimization is applied to the smooth problem. Optimization algorithms are applied to the smooth problem. And then we need to further consider the approximation error. Okay, so this is everything about smoothing. In the end, our solution our algorithm is still the same algorithm, it's accelerated gradient descent algorithm. But when we implement this algorithm with a smoothed function, we need to calculate this gradient. It's the gradient of the smoothed f. So the first step is you need to figure out how to smooth your objective function and what is the gradient of the smoothed function. Okay, and this is everything about lecture 7, the smoothing technique. And I think we don't have we do not have a homework for lecture 7. So you can spend more time on the previous homeworks. So homework 7 would be, let's see. This is the accelerated algorithm. We already talked about that. Yeah, okay. Homework 8 is a big project on video surveillance, but I think for this one we will need the following 2 lectures. Yeah. Wins 8 and 9. So let's dive into the lecture 8. Primal dual and primal dual methods. So here we will talk about a very important concept called dual form of optimization problems. So in the previous lectures, we are designing algorithms in the primal form. Primal form basically refers to the original problem, the original optimization problem that we are looking at. And in this lecture, we will see that in many cases, we can transform these problems to another form. And that will lead us to the dual methods, development of dual methods. It's similar to the Fourier transform and all those kinds of transforms where we transform the signals from one space to another space, and we can see a different picture. And we will mainly talk about 2 algorithms. One is the dual proximal gradient method. From the name, we can tell that it is the proximal gradient method applied to the dual form of the optimization problem. So we will have to introduce this dual form first. And the second algorithm is primal dual proximal gradient method, which means that this algorithm is kind of switching between primal form and dual form alternatively. And here we will consider a more general class of optimization problems, which we call the constrained optimization, constrained convex optimization. And specifically, we consider this problem. We are minimizing a convex function f subject to a linear constraint, where the constraint says that ax plus b AX plus B is a linear transformation applied to the affine transformation applied to the vector X. So this vector AX plus B belongs to a certain convex set. And to solve this problem, we can just apply the some of the previous algorithms that we developed. For example, projected gradient descent. Right, we do a gradient descent on F and then project the solution to this constraint set. However, this requires that we have a good understanding of that projection. So the projection, sometimes if the projection is very hard to compute, then this method is very hard to implement. And the other thing is that sometimes F may not be differentiable. So more generally, we consider this composite form, which is minimize fx plus hax. And this form generalizes the previous constraint form, because we can simply write this constraint as an indicator function. But we have mentioned this many times. In optimization, we can treat constraints as a kind of indicator function. So this problem can be written as fx plus the indicator of ax plus b belongs to C. This is an indicator function. So this indicator is 1. Oh, sorry, this indicator is 0 if this condition is met. Otherwise, it will be positive infinity. So this indicator function is what we call hax. The convex function if this constraint set C is convex. Okay. So we consider this form instead of the constraint form. If F is indicator, then we get the constraint form. But in general, F can be an arbitrary convex function. And we can do proximal gradient descent because it's a composite optimization problem, right? So if you view this as the regularizer, then we can do a proximal gradient. Gradient descent on F, and then we need to evaluate the proximal mapping associated with H. Right? However, this evaluating the proximal operator of this function can be hard, even when this H is a simple function. For example, if H is L1 norm, then this is L1 norm of A times X. And this is very difficult to compute because this matrix A, in general, it will couple all the coordinates of X together. So it is very hard to get an analytical solution. Right. So computing proximal of H can be simple. Okay. But computing proximal operator of H composite with a linear mapping, this can be very difficult. Like in this case, it's H of A times X. This linear mapping, this A will this transformation in general, it will make all the coordinates of x correlated. Okay, so this motivates us to develop to kind of simplify this problem. Try to get rid of this linear transformation, affine transformation inside this H function. So what we can do is to introduce a equality constraint. So looking at fx plus h of ax, we can define ax to be an auxiliary variable z. And then we just need to add such a equality constraint. So these two problems are equivalent because of that equality constraint, right? Subject to z equals to ax. So essentially, we are working on the original problem. And then by introducing this auxiliary variable z, we kind of decouple this x and ax in the objective function. So now the affine transformation is only imposed on the equality constraint. But in the problem, x and z, they are two different things. We just need to make sure they satisfy these equality constraints. And then in the following, we define the dual formulation of this equality constraint reformulation as follows. This is a reformulation, right? We reformulate the original problem into an equality constraint problem. So from here, it is easy to see they are equivalent. And then for this equality constraint form, we further define the dual formulation as follows. It's basically, the idea is very straightforward. We keep this the minimization part of the objective function, right? It's this part. And then we move this equality constraint, move it into the objective function by multiplying with a parameter, a vector lambda. So we do ax minus z multiplied by lambda. And then so how do we address this lambda? Lambda is another auxiliary variable that we introduced. We call it the multiplier. And we will consider maximizing this entire problem over lambda. So what you can view the inner problem. For example, for every fixed lambda, we can consider this inner minimization problem. If lambda is fixed, then this is a valid optimization problem. I can minimize over f and z. Okay, so for every lambda, I can do the inner minimization. And then outside this inner minimization, we further maximize over lambda. So we further maximize over lambda. So Actually, this dual formulation is related to the Lagrangian multiplier method. So what we usually do is this one. So let's look at this problem first. It's minimize fx plus hz subject to ax equals to z. Right. This is exactly the original optimization problem. So there's no difference. No difference between the two. And then we can further take one step further. We can do the following. I can put this constraint into the objective function. So I put this constraint into the objective function by adding this linear term, by adding this inner product term, inner product between lambda and ax minus z. Again, I introduce this multiplier lambda, but here, before I take minimization over x and z, I first do a maximization over lambda. And I claim that these two are equivalent. They are exactly equivalent. Why? Because looking at this part, we can have two cases. Okay. The first case is okay. For a fixed x and z, for a given x and z, we can look at this inner maximization problem. Right? If you give me an x, give me a z, I can look at this inner maximization problem. I can maximize over lambda. Fix x and z. Now, for a fixed x and z, we have two cases. First case is ax equals to z. If this x and z happen to satisfy this linear equality constraint, then the inner maximization problem is for the lambda terms, lambda times 0. So it's essentially this inner maximization essentially equals to fx plus hz. The other case is that if they are not equivalent, which means ax minus z is something non-zero, and this is a linear term over lambda. Lambda is unconstrained, so there's always a way to choose a lambda so that this inner product goes to positive infinity. Okay, so in that case, it's positive infinity. Right. So you see the inner problem, the red part, the inner problem is essentially equal to this one. And if you look at this, these two, it's essentially the original constraint optimization problem. Right. If this constraint is satisfied, we are minimizing f plus hz. If it's not satisfied, then everything is positive infinity. We don't care. Right? We don't care about those bars. So it is equivalent to the original constraint form. Okay. So you see how this lambda is introduced by moving this constraint into this objective function. Okay. Then we can introduce this multiplier lambda and then introduce this inner product term. Right. So up to this step, we have shown that the original problem, this problem, equals this constraint form, and this constraint form equals this multiplier form, this min-max form. Min-max. So these three are equivalent. And this dual formulation is basically switching the order between this min and max, right? So in this equivalent form, we are doing max first. Right, so the maximization is inside, and then outside we have minimization. But in the dual form, we kind of switch the order of this min and max. We do min first, and max follows. And there's a question like, can we switch these two for free? Are they still equivalent? And turns out not. Under some conditions, they would be equivalent. Right? So basically, for convex problems, we can confidently switch the order, but in general, it does not hold. Okay. So that is the motivation of defining this dual formulation. We start from the original problem, move it to the reformulate it as the constraint version. Now the constraint version further reformulated it as this multiplier version. And then this multiplier version, we can consider switch the order between these two. Okay. Under some conditions, these two are equivalent. It doesn't matter if you do min-max or max-min. Okay, under some conditions. And this would be the dual formulation that we consider for this problem. Okay, so let's look at this dual formulation. So basically, the way we can understand it as this way. Once we have such a optimization problem, A, F, and H, they are convex. Both of them are convex. Then we can consider this dual formulation. We can consider this dual formulation. The nice thing about the dual formulation may look a bit complicated, but the nice thing is that in this formulation, Fx, Hz, they are decoupled. Right? It's different from the primal formulation. Ax, these two x, this x is coupled by A, but here it's just x and z. The real coupling is now inside this inner product. So we kind of decouple these parameters. But the question is, how can we understand this dual formulation? Because it looks a bit complicated. Previously, we have minimization only. Now we have an extreme maximization. So let's look at this dual formulation. Now, first of all, we can, for the inner minimization part, we can decompose this into minimization over X and minimization over Z, because this we can simply decompose this inner product term into two parts, right? AX times lambda and the Z times lambda. And then we put everything about X in one part, put everything about Z in another part. So we can do the minimization separately. So it's just a rearrangement of these terms. Now, if you look at these two minimizations, they are exactly the definition of conjugate function that we introduced last time. Right, so just recall the conjugate function of f evaluated at x is defined as sup over z times x minus f z. This is the definition. Then, for example, the second term can be viewed as negative h conjugate lambda, because the minimization of this one is like I can do is the maximization of the negative of this term. I can do this part. Minimization hz minus lambda z is the maximization of lambda z minus hz and the negative. And then this, now compare with this definition, this is h star lambda. H star lambda. So we have negative h star lambda. Right, so always the dual form is always connected to the conjugation. And for the first term, we do the same thing. So it's negative f star, negative a transpose lambda. Okay, just rewrite it into this standard form, and you will see that this f star h star is what we call the conjugate function, the differential conjugate function. And then you see that now this problem becomes a maximization problem, right? Becomes a maximization problem over lambda. So this is called the dual form of this of the prime associated with the primal primal form. Right, so the dual form we start from here, and turns out that can be rewritten in a compact form, in such a dual form. And this dual form is So in this dual form, we are working on the multiplier. We are optimizing over multiplier lambda, and the functions become conjugate, f conjugate and h conjugate. So here we rewrite, because this maximization of negative f star minus h star, so we can pull this negative sign out and instead consider minimization. So that's why we have this minimization over lambda here. So this is the dual form of this primal problem. And the interesting part is that, as we discussed before, if we want to apply proximal gradient method to the primal form, right, the challenge is to evaluate this proximal mapping. This can be very difficult because of the mapping A. But now in the dual form, this A is inside F star instead of H star, right? So this seems to be easier to work with the proximal gradient method. So we can consider apply proximal gradient method to the dual form, to the dual problem. And then to do that, we can see that we will need to compute the proximal mapping associated with H star. Okay, and this can be done easily through this moral decomposition that we talked about before. So the proximal mapping of H star equals to X minus the proximal mapping of H. So essentially, if the proximal mapping of H is very cheap, very simple, then we can also compute the proximal mapping of H star very easily. So this part in the dual form, it is sometimes, right, this H star is very easy to handle using the proximal gradient method. And for the F star, for this part, we can do proximal gradient descent if this F star function is smooth. Okay. Now, if this function is smooth, that equivalently means that the original function f is strongly convex. Therefore, if you have a, so this is this is the trade-off between like primal and dual form. Sometimes problems are easier in the primal form, sometimes they are easier in the dual form. So in this case, suppose in your primal form you have a strongly convex f, but this term is very hard to handle. Right? This H can be very simple, non-differentiable, but because of the linear mapping, you cannot compute the proximal mapping of this function. So you can consider dual form, and then in the dual form, you just need to consider the proximal mapping of H star. Well, it is given by the proximal mapping of H. Okay, so you can do proximal gradient in the dual formulation. Okay. So the idea, dual proximal gradient method, very simple. Apply proximal gradient to this problem. We apply proximal gradient descent to this problem. So we are doing, inside is a gradient descent. Now this is a plus instead of minus, because once you take the gradient by the composition rule, there's a negative sign coming out. There's a negative A coming out. So this is plus instead of minus. And then outside we do proximal mapping over associated with the function H star. So this is simply exactly the proximal gradient method applied to the dual problem, nothing else. And then by this convergence guarantee of proximal gradient method, we know that this method converges at the rate 1/t. Assuming that this is a convex smooth part, this is another convex part, so that we can apply the standard proximal gradient descent result. So this is the dual proximal gradient method, and to apply this method, we just need to figure out this how to compute this gradient of the conjugate function and the proximal mapping of the H star function. We'll talk about this part later, but this is the kind of the abstract high-level idea of developing these methods. Okay, and in optimization, we will see this is the essential idea of optimization. Sometimes with the problems it's easier, but sometimes the primal problem is very complicated. So we can consider a dual formulation. And this update rule, this is a standard proximal gradient update rule applied to the dual problem. And because of the conjugate functions, here is conjugate f, here is conjugate h, we can rewrite this update rule into a more explicit form that involves only the primal functions. So this 9.2, this is the equivalent formulation of the previous algorithm. It's an equivalent form of the dual proximal gradient algorithm, but it is written in a primal representation. So all the updates, you only see f and h instead of f star and h star. But the algorithm updates are they look very different because it is now represented in the primal form. So the first update is xt is basically given lambda t. We solve xt. We get xt by solving this this problem. So fx plus this linear term, this multiplier term, and then we update this lambda t by this step. And in this step, it involves this linear transformation and also involves this proximal mapping. And this proximal mapping only depends on the function h. Yeah, and we have some proof or justification of this. So it is not clear how to rewrite this single line of update into 2 lines of updates. Especially how to get rid of this f star and h star. So so let's look at these updates. Okay, so I think we are going to look at this one. Okay. Let's look at this equivalent form and see how it from here how these two updates can match the previous update and match this one. So from this form, xt is defined as the minimizer of this problem. So by the optimality condition, we can claim that 0 belongs to the subdifferential of the right-hand side. The right-hand side is subdifferential of fx plus a transpose lambda t. And basically, you take the gradient and set it to 0. That's the optimality condition. And from here, from this, we can get this inclusion property, right? So negative a transpose lambda t belongs to the subdifferential of fxt. So this is what you get from the first line of update. And this result, together with the conjugate subgradient theorem and the smoothness of f star. So these two are, here we assume f star is smooth. But this conjugate subgradient theorem, we haven't talked about it, but essentially what this theorem says is that once we have this inclusion property, so you see this vector on the left-hand side belongs to the subdifferential of f at xt. Then we can kind of take the inverse. We can move this subdifferential to the left-hand side and solve for xt. So by this conjugate subgradient theorem, we can do that. However, when you move this to the left-hand side, this f must becomes conjugate. Right. So from this inclusion property, we get this line. So this xt is actually the gradient of f conjugate evaluated at that point. And based on this one, so therefore this gradient of conjugate of f term is actually this xt, right? So then we can plug this one into this update rule. So this gradient term would be xt, would be that xt. So instead we will just have lambda t plus beta t a times xt. Okay? So therefore this line of update simply reduces to this one. And then we completely get rid of this f conjugate. And next we will need to get rid of this h conjugate. From the Moreau decomposition, from the extended Moreau decomposition, the proximal mapping of h star, of eta h star at this point is equal to the right-hand side. This is the Moreau decomposition. If you view this as another parameter k, is this k minus the proximal mapping evaluated at this k, right? And there are some parameters you need to pay attention to. But this is essentially the form of Moreau decomposition. And here h star, right? On the right-hand side, we don't have h star. We don't only have h. We only have h. Therefore, this is the lambda t plus 1 we get from the first algorithm. And so therefore, this is lambda t plus 1. The left-hand side equals to the right-hand side. And for the right-hand side, we can rewrite it. It's basically this one. So this is a rewrite of this algorithm in a primal form. Therefore, when you implement the dual proximal gradient method, you can actually implement this one instead. This looks more clear to understand. In the first line, you solve a optimization problem. If f is differentiable, you can probably solve it by gradient methods. In the second line, it's just a numerical update. So the as long as you can compute this proximal mapping of H efficiently, then you can do second line very quickly. But here in the first line, depending on the form of f, you may need to implement another algorithm to solve the first problem, because the first line is an optimization problem. Okay. So this is the dual proximal gradient method. So we start from this. We are interested in this optimization problem, but it can be very difficult in the primal form. So we transform it into the dual form. But the dual form, the nice thing about dual form is that we get rid of this A in this H. Right? This matrix A is in the first term now. But then both F and H now becomes conjugate functions. And this conjugate function can be hard to compute in some cases. But so the dual proximal gradient method is simply applying proximal gradient to this dual formulation. And it turns out that such an update rule can be rewritten into a primal representation form. Well, this H star and F star can be translated into this these updates. You can sort of see that in this minimization problem is essentially something about the conjugate of f, because that's how we define the conjugate function. That's how we define the conjugate function. And the second step is basically a proximal gradient type step. It's from the Moreau decomposition. Okay. So this is the basic algorithm, basic proximal gradient algorithm applied to the dual form. And in practice, we have to solve this problem first. And this could be a bottleneck for this approach. So later on, we will see some other approaches that can avoid this solving these sub problems. Okay, I think I will stop here today. This is the dual proximal gradient method. Next time we can talk about briefly talk about the analysis of this algorithm. Okay, I will see you guys next week.